Okay. Yesterday we walked through some solution problems. I want to discriminate now between two ways to make a solution. Yesterday was the dry process. Dry meaning we added dry powder of the solute into the water solvent. Today we're going to take and dilute a concentrated solution. In other words, if we're making a salt solution, we're going to start with a really concentrated brine, like 24 molar brine or whatever. Then we're going to dilute it down to the appropriate diluted level. But then there's some calculations involving is how much of the concentrate we need and all this stuff. Okay. Now, this concentrated form is used almost as much as the dry. In the stock room, all acids come concentrated. Usually in the form of 12 to 18 molar. Really, really strong. And then you dilute it down to whatever we need. Like today we need 3 molar hydrochloric and some 6 molar hydrochloric. So we're going to take the 18 molar or the 12, whatever they vary, depending on which acid we're talking about, down to the appropriate diluted level. So it's used a lot. The pool group, when they go out and test your pool, sometimes they add concentrated chlorine base. Sometimes they add dry pellets, so it varies. These two methods are very, very ubiquitous. They're all over the place. Okay. So yesterday we talked about how do you make this much solution at this concentration by adding dry ingredients. And we're going to do the same thing today, only adding, we're going to take and dilute concentrated ingredients. Now, this is very weird. I sound like I'm screaming to you right now because my ears are plugged. And I'm kidding. So, am I talking at appropriate level?
Yes.
Okay. All right. So, the process, dry, we're adding dry ingredients to solvent less than the final volume. Excuse me. And then we brought it up to final volume after the dry stuff dissolved. The wet one is we're going to add enough water to a concentrated solution to bring it up to final volume. Now, it may seem easier. Well, you overcome that process of Archimedes' principle where when you add the dry stuff, the volume goes up. We don't have that problem at all with the wet process. Okay, so let's look at a problem. Okay, so we need to review one important concept here. Now, remember I said, remember this? It's concentration times volume. And this is typically in moles per liter. And this is in liters equals moles. Now, this works on the back end of the dry part and in the front end of the wet process. Okay, so first of all, let's talk about the concept here. Okay, if I start with 5 molecules of salt, common table salt, sodium chloride, and say this is 2 liters. And then I take excuse me again, 5 liters of water and add it to that. Okay, question is, does the number of molecules of salt change? No. We start with 5, we end up with 5. What's changed? Yeah, the solvent, basically, amount of water, solvent. That's the only thing that changed. So we're talking about, so let's say, okay, so if we take the 2 liters of water with 5 molecules of salt, and then we add 3 liters of water, our total now volume is going to be 5 liters, but 5 molecules of salt. Okay, that means that the number of molecules stays the same, 5 to 5. Solvents change, but not the number of molecules. So number of molecules is the same as moles. So we have an initial moles equals final moles. And we're going to use this relationship up here. So instead of moles, we're gonna write concentration times liters equals, this is initial, so the initial concentration times the initial volume equals the final concentration times the final volume. Okay, so our final volume is, in this case, unknown. Excuse me, not the final volume, the final volume is going to be 12.3. What we don't know is the initial volume of the concentrated stuff. So we know the initial concentration is 14.7. That's equal to the final volume is 12.3. And the final concentration is 2.34. Okay, does everyone see where those numbers came from? You got 4 variables. I have to give you 3. Solve the 4th. So the 3 volumes, or the 3 unknowns are concentration of what you're starting with, the concentrated stuff, the volume of the concentrated stuff, the volume of the initial stuff, which is the concentrated stuff, and the final volume, concentration, the 4 variables. Okay, so how do we do this problem? How do I solve for how much concentrated solution I'm going to add? Say what?
Divided by 14.7.
We're gonna isolate the initial volume. Okay, to do that, we divide both sides by 14.7. Those cancel, gives us the initial volume. Initial volume again is the concentrated stuff. And then we're gonna grind this out over here. Okay, so we're gonna take, now these are the instructions, how to make. Now, how much water are we gonna add? We've already got 1.96 liters of the concentrate. What's the final volume? One point 3 liters, right? Now we've added to that already 1.96. So how do we figure out how much water we need to add? Exactly. We subtract. We've already added 196. So we take that from the 14.7, excuse me, from the 12.3, and that'll give us how much water to add. So we're going to take, let's see here. Total volume minus the 196 of the concentrate. And we're going to be at hey, does everyone see why I got the 1003 liters of water? Our total volume is 12.3. The concentrate has taken up 1.96 of that 12. What's remaining is how much water we got to add. How much do we have to dilute that concentrated stuff to get up to proper concentration? So over here now, okay, so we're going to add 196 liters of concentrated salt solution to a container plus 1003 liters of water and stir. Yeah.
I got 10.34.
On which one?
Oh,
1.03. Are you talking about the subtraction part?
I got 10.34.
Yeah, 10.34. Okay. All right, does that make sense? It hinges upon the fact that the moles don't change. The initial moles equals the final mole. Change is the volume of the solvent.
Since it's like an actual solution, does that mean the significant figures doesn't apply to it?
Say again?
You know, like significant figures, like, you would like round it to like, 10.3. So, since it's like an actual solution and we want it to be exactly
Yeah.
12.3, we don't do that.
The problem is the decimal place. We get significant figures, adding, subtracting, we look at decimal places only. 1 versus 2, so it should be 10.3. Yes. Yes. The reason I didn't do that is for clarity. If I wrote 10.3 there, I got 10.3. Sorry. But yes, you're absolutely right. Should be 10.3 if we're looking at sig figs. Okay, let's do another one. Now this is a historical one. In fact, I had this on numerous tests. Okay. You are a person that loves animals. I know all of you, some of you are more loving of animals than others, but so you had a collection of hamsters at your house. Okay. And you wanted to treat a hamster to a spa. So we have our little hamster. And so you go to the store, go to PetSmart or whatever, and you ask the guy, where is the spa treatment for hamsters? Aisle 9. Yeah, you go down to aisle 9 and you're looking and you get this wall of, the typical, all these different concoctions. Some are wet, some are concentrated, and some are dry. Okay, so according to the net, the ideal spa concentration for rodents is 3.33 molarity. That's the perfect concentration for rodents, i.e. your hamster. Okay, and your little hamster hot tub is 6 liters. And it's a saline spa. Okay. So let's do this dry and we're going to do it wet. Okay. So we pick up a box of table salt that's specific for hamsters, not any old table salt. This comes from the dry lake bed in Utah. Okay, so we have grams in a box. Okay, so how do we make this spa concoction? Well, first of all, how many moles do we have? Well, moles of salt is gonna be 6 liters times the concentration again. Let's see. Actually, it's 2 moles. So how many grams is 2 moles of salt? Well, I think we did this yesterday. $58.44. Okay. Okay. So the directions are okay, so we're gonna add 117 grams of table salt to 5 liters of water, or 4.5, or 5.5, yeah. Where did I get what? 3.33? That's the concentration of the spa water. Does that make sense?
I think what you're trying to say is that 6 times 3.33 is 19.98, rounded up to 20. Instead of 2.
Oh, I see. Okay, it's gonna be 1170 grams of solvent. So down here. Okay, so that's the dry approach. Okay, dry approach gives us what we want. It's fine. So let's label that as dry. Okay, so let's look at the wet approach now. Okay, so we've got okay, at the store, the concentrated brine comes as 23.9 moles per liter. Okay, so let's set up our equation. So the initial conditions, final conditions. Okay, the initial conditions are we've got the concentration of 23.9 molar times, we don't know what the initial volume is yet. We're going to calculate that. That's how much of the brine we're going to add to the final solution. And that's for the final, it's going to be 633. So this is the initial volume, oops, not initial. Okay, so what we don't know are the liters of the concentrated stuff, the V sub I. So divide both sides by 23.9. So the initial brine solution is going to be okay, so we're looking at 0.14 liters. So our directions are
Professor, how did you get the 0.14?
I got
Because I'm getting a
0.83.
0.83.
Okay, I got the same thing.
So
If we're rounding, it would be
0.87. Oh, yeah.
oh, you're right. Instead of 3.33, I added
The 3.3.
0.336. Yes.
So I got 0.84 if we're rounding it.
For the initial volume.
0.84.
Okay, well, let me do this. Okay, how do we figure out how much water to add? Okay, our final volume is, what, 6? That's gonna be 6 minus. Okay, so sig figs is gonna be 2 sig figs because it's 2 decimal places. So looking at 5.6 liters water. Okay, you're gonna add 0.836 liters of concentrated salt solution to the 5.16 liters of water and stir. We'll end up with 6 liters of our 3.33 milliliter moles per liter concentration. That makes sense? Okay, so that's the 2 major ways to make solution. Now, if you're applying for a lab tech job or a professor's job, depending on the school, you have to actually go in the library and prepare stuff. It's one thing to talk about it, it's another thing to actually do it. So it's a practical interview, very interesting. Sierra is very formal. It's like unreal formalized. Here, not so much. Just, it varies by school. How I got hired up in Tacoma, I was in Mexico. And my friend, I was teaching high school at the time, my friend calls me up and says, Tom, we desperately need someone to teach chem over the summer at Tacoma Community College. I said, Leo, I'm in Mexico now. He said, we'll take care of that. They were desperate. Apparently, the guy that was supposed to teach it at the last second said, sorry. And so anyway, they got a substitute for me for 2 weeks and I came in and that was my interview. Or lack thereof. So it really varies. Okay, all right, so I'm gonna cover one more thing today. Assuming I get over this coughing fit. Okay, so what if we have 2 solutions? And let's say this is table salt. Okay. And we dump them together. What's our final concentration? Okay, so a couple ways to look at this. We have moles, let's call this A, B. We have moles A, moles B. When we add those together, Um, hmm. How many moles do we have total? A plus B, right?
Hmm.
We have 5 and 1, 7 and another, add them together, that's it. Okay, next is volume. What's the total volume? Volume A plus volume B. So now we have concentration. Final concentration is A plus B over A plus B liters moles. Does that make sense? And then we just do it. Okay, so. All right, so we're going to take 5.0 liters times concentration plus 3 liters times the concentration is 251. Okay, so this is A, B. Okay, so we're going to add these two together to get the total moles of our mixture. So let's see, 7, 8. Okay, volume. We have 5 liters, 3 liters. Gosh, do I need my calculator?
Mhm.
Okay, now we got moles per liter. Okay, so our new combination is kind of halfway between the two, 1.5 and the 2.5, 194 moles per liter. Okay, does that make sense?
Professor, we're just adding the 7.80 and the 7.53, right? I'm getting 15.33.
15 point what?
33.
Well, that's what I got too. I need to have all you guys check my work. Okay, so it's going to be not 194 though. Close to that, but not. Okay, so basically, we're adding the moles, we're adding the volume of the new stuff, and then creating a new concentration. Now, when we get to acids and bases, we're gonna do the same calculation. Only when you add an acid and a base together, you get a neutralization reaction. So some of the constituents are taken out through the neutralization. And then you get to see what's left over. Is it on the alkaline side or the acidic side? But it's basically this set of calculations with a neutralization thrown in there. Okay, are there any questions about this other than my transcription? Okay, so what we're gonna do is, let's see, what are the other little ways to do this? Well, I can do a combination of this. Let's do one more, and that'll be it for today. Okay, so solution A is 6 liters, 1.57 moles per liter. And solution B is we added okay. So in A, we've have a solution. B, we created a solution by adding 4.5 grams of salt to with a final volume of 4.0. So if we add them together, it's the same process. Moles plus mole, volume plus volume. Okay, so let's do the moles first. Okay, so if we already know the concentration and the volume, we can calculate moles simply by adding, so multiplying them together. Okay, if we don't know the concentration, but we know how much dry solid was added, we can calculate that. Okay, so we have times the molar mass of salt, which is what, 5844? Okay, and then we have volume, 6, 4. I'm taking a wild chance and say it's 10. You guys check me on that now. So whether you start with liquid or you start with dry, it's still moles plus moles over volume plus volume. Now, a lot of people really get hung up on this kind of problem when you're adding two together. If you approach it like the moles have to add up, the volume has to add up. And then we just crunch it out at the end, make sure it's moles per 1 liter. Okay, any questions about this?
So we would need to convert grams to grams in order to solve this solution.
Yeah, because we started with grams and we need to go to moles, just using the molar math. Okay, that's what I wanted to cover today. And